Swayam Prabha. Digital India. Educated India.
Welcome back to lecture number 11, part 1 on the topic condenser. In the previous lecture, we have seen the first major component of a vapor compression refrigeration system, which is the compressor. So let us see the construction working principle and a couple of numericals in the topic condenser. So condenser is a heat exchanger. It's a device which is a heat exchanger which is used to condense the refrigerant. Process of condensation takes place. High pressure, high temperature refrigerant from the compressor enters the condenser where it undergoes phase change from vapor to liquid. During the process, heat is rejected to the medium. The medium could be either air or water. Normally, air cooling is preferred for small capacity systems, and medium and large capacity systems are water cooled. So it is a heat exchange in which the refrigerant undergoes phase change from vapor to liquid. In a typical condenser, the refrigerant enters the condenser in a superheated condition. The heat is rejected to the sink, as I told, heat sink, which could be either water or air. In the first module, while solving numericals, we have solved almost 5 to 6 numerical questions. In every question, I have plotted the temperature and entropy diagram and the pressure enthalpy diagram. So we have mentioned the process. 1 to 2 is isentropic compression. 2 to 3 is condensation process. So here I have taken the portion of the condensation process, that is, which is there after the compression process. So 1 to 2 is, this is isentropic compression. Okay, so this is isentropic. Now from 2 to 2 dash, so as I said before, in a typical condenser, the state of the refrigerant after compression is superheated condition. From 2 to 2 dash is lying on the saturated vapor line, and 2 is in superheated condition. So this is in superheated condition. Superheated state. This is superheated. So from 2 to 2 dash, it is called de-superheating. De-superheating is nothing but a process during which a gas is cooled close to the saturation. So this is superheated condition. So from 2, the refrigerant, the high pressure, high temperature refrigerant vapor is cooled close to its saturation. So then from 2 dash, the condensation, the phase change occurs. So 2 dash to 3 is condensation, 2 to 2 dash is called de-superheating. Now the challenge is whether the refrigerant condition at the outlet of the condenser, is it saturated liquid or subcooled? There are 2 factors which decide the condition of refrigerant at the outlet of the condenser. So let me move to the next one. So where I have shown the subcooling, this is de-superheating. 1 to 2 is isentropic compression, so the WCO. 2 to 2 dash is de-superheating, 2 dash to 3 is condensation. In the previous diagram, I have shown the process without subcooling, and this one is with subcooling. So which factor decides whether the refrigerant will leave the condenser as subcooled liquid or saturated liquid? There are 2 factors which will decide this one. Number 1, the temperature of the cooling medium. That is the sink, heat sink. And the second one is the design of the condenser. So the condenser design and the temperature of the cooling medium decides whether the refrigerant will leave as a subcooled liquid or saturated liquid. And 3 refers to the end of the condensation process, that is phase change from vapor to liquid. Then there is a subcooling. Okay, we have solved one problem in the previous lecture where the degree of subcooling was around 6 degrees centigrade. 6 degree centigrade. Let us see the classification based on the external medium. The condensers are classified into air cooled and water cooled. Okay, so of course we have a combination of air and water also. That is in case of an evaporative condenser. So again, in air cooled, we have 2 categories: natural convection and forced convection. Natural convection and forced convection. So we will see the construction and working of each of these types. This is the natural convection type. The natural convection, the process takes place due to density gradient. Due to density gradient, it is a natural phenomenon. All of us, when there is a difference in the density, the hot fluid rises up and the cold fluid will be at the bottom. So hot fluid tend to rise. And these are all the fins are used. These are all like the fins. Refrigerant is entering and it is going through the tubes and it is leaving. So the air is circulated. Of course, it is not by any external device. Here in natural convection, it flows naturally. As much as possible, the fins are to be placed wider, not too closer, so that the air can flow freely with little or with less resistance. With less resistance. Definitely, there will be resistance to the flow, which cannot be eliminated, but the fins are to be spaced somewhat wider so that the resistance to airflow is minimized. So due to density different gradient, the flow takes place, and the refrigerant, the condensation. Okay, so the condensation process, vapor refrigerant is converted into liquid refrigerant, and the heat is removed by the. So the heat transfer coefficient in case of natural convection is small, since the airflow rate and the radiation heat transfer rate are not high. Okay, compared to forced convection. This type of heat convection, natural convection, requires a large heat transfer area, and normally these are employed for small capacity systems, refrigeration system. So normally, if you take a natural convection type, there are 2 subcategories: finned tube type and plate surface type. Finned tube type and plate surface type. So in case of a finned tube type, normally it is like, the refrigerant flows inside the tubes and the fins are there. The condenser is placed normally, this is normally used in refrigerators and all, okay, smaller capacity units, where the condenser is fixed at a particular angle, or normally it is placed on the rear side of the refrigerator. And in case of plate surface type, the refrigerant is carried inside in the tubes, which the tubes are attached to the walls of the refrigerator. Of course, there is insulation is provided between the inner surface and the outer walls, between the inner and the outer wall. That is the difference between finned tube and plate surface type. Natural convection, type, condenser. So there are 2 types. One is finned tube type. Another one is plate surface plate. Plate surface. Next, forced convection, as the name indicates, an external device. Okay, like a blower is used to circulate the air. So when we use an external device, the heat transfer coefficient is more than that of a natural convection. So a blower, you can see the air is circulated over the tubes, the refrigerant is passing. Okay, so here also I think this is, so the refrigerant enters this one and it is, the heat is removed by the air. So this is the air inlet portion and this is the air outlet. Hot air comes this side. So we can see in the window AC or on the outdoor unit of the split AC where the condenser is cooled by air. We can, if we see, just stand outside the window AC, the exterior portion. So if we keep the hand near that condenser portion, we can see, since the air is hot, so that is the heat rejected by the coolant during the condensation process. So circulation of air by fan or blower, 2 to 3, 4 meter per second. Fins are used for better heat transfer, that is to enhance the heat transfer rate. Air flow rate is normally 15 to 35 meter cube per minute. Normal air side temperature differences around 15 degrees centigrade. These are employed for window and split air conditioners. So if you see the next category of classification, this is based on the, based on the external medium. First category is air cooled. Under air cooled, we are having natural convection and forced convection. In natural convection, fin tube type and plate surface type are there. Now, the second classification based on the external medium is water cooled condenser. Under water cooled, we are having shell and tube, shell and coil, double pipe. Let us see the construction. So shell and tube heat exchanger. Okay, we have a shell portion and a tube portion. This is the shell portion. Okay, this is the shell portion, and the tube is inside the shell. Refrigerant enters. This is the inlet of the tube portion where the refrigerant enters and it leaves as liquid here. Coolant, that is normally the water which is used, it is enters this one. And if you see the direction of flow, it is the refrigerant is flowing from left side to right side, and the coolant is coming entering at the top and it is moving towards the left. So the directions are opposite. So that is counterflow. Counterflow arrangement has, the efficiency is better compared to parallel flow. That is, both the hot fluid and the cold fluid are circulated in the opposite direction in case of counterflow. So the both hot and cold fluids circulated in opposite direction. That is counterflow. If it is a parallel flow, both cold and hot fluid enters in, the flow is in the same direction. The shell and coil, instead of a tube, we have a coil. Okay, we have a coil. The refrigerant is entering on the shell side and at the top and leaving at the bottom. Coolant is entering through the tube and it is circulated through the tubes and this one. Here also you can see the direction is opposite. So it's a counterflow arrangement. Next one is double pipe. As the name indicates, there is a pipe inside a pipe. There's a pipe inside a pipe. So this is pipe 1, that is the outer pipe, and this is the inner pipe. So the coolant is flowing through the inner pipe as per the schematic shown, and it comes out as hot. This is the cold fluid inlet. It takes the heat during condensation process and comes out as, this is the cold fluid outlet. Okay, the cold fluid is being heated and the hot fluid is being cooled. So refrigerant enters at the top and it travels through the annulus, this one, and it comes out. Evaporative condenser. So this is like, it's like a combination of both air and water. So here you can see the refrigerant is entering through the tubes Okay, there is a nozzle to spray the water, which is pumped from the bottom. Water, this is like this portion is the water sump, where water is pumped with the help of pump, and it is sprayed like a fine droplets with the help of the nozzle. And in this portion, the air is circulated, air is entering. So both, it is like, I mean, both the cooling medium are used here, and the hot air, after it removes the cooling the liquid, it comes out. So this is air inlet, this is air outlet, and this is water inlet, and this is the water outlet, but it is sprayed through the nozzle. Compared to all the constructions that we have seen, evaporative condenser is energy efficient. Both the coolants are used to remove the heat from the condensing refrigerant. It's a combination of a cooling tower and a water-cooled condenser. So drift eliminators, though it is not shown, it is used in the construction. It restricts the water carryover, and there is a float wall which maintains the level of water in the sump. So this portion is the water sump. Okay, water sump, float wall. It is used to regulate and maintain the level of water. Now let us compare air-cooled condenser, water-cooled condenser. So construction is simple. Only a fan is, in case of forced circulation, fan is used. In case of the construction is very simple. It does not require any pipings or pipelines, etc. Whereas water-cooled condenser requires piping. Maintenance is easier in case of air-cooled condenser. Maintenance is a issue in case of water-cooled, because most of the places the water contains a lot of salt. So there are chances of scaling the condenser tubes when we use water as the cooling medium. Scaling issues or scaling problem is there. So we need to clean the condenser tubes. The maintenance is required. And normally air-cooled condensers, as I told before, they are employed for small capacity systems, whereas for medium and large capacity systems, water-cooled condenser is used. Since the components are very less in air-cooled condenser, the initial cost is less, and operating cost is also much less. Only a fan is there in case of forced circulation. But in case of water-cooled condenser, I mean, pump is required, like a supply pump and return water pump. Then pipelines are required. The initial cost is more, and the operating cost is also more. Of course, I mean, air is available easily in all the places. There are places water scarcity are there. The COP, of course, the main advantage of a water-cooled condenser is the COP increases due to low condensing temperature, whereas in case of air-cooled condenser, the COP is less. There's a term called heat rejection ratio. So it is the ratio of, let me go to the heat rejection ratio. It's a very important term. HRR. It is the ratio of heat rejected. Let us see this one. Heat rejected to the refrigerating effect. Heat rejected to refrigerating effect. Heat rejected by the condenser is normally Q suffix C, and refrigerating effect is QE. Now, if we see the energy balance, the summation of evaporator heat load or cooling capacity, that is QE, and work of compression is equal to QC. QC is nothing but QE plus WCO. We have seen this one in the energy balance. So, divided by QE. If you divide, you will get 1 plus WCO by QE. And WCO by Q, the ratio of refrigerating effect to work of compression is called COP. And this is the other way, reciprocal. So, it is, this term is 1 by COP. So, this is equal to 1 plus 1 by COP. So, that is, therefore, HRR is equal to 1 plus 1 by COP. So, that's what I have written. Okay. So, that's what I have written here. And one more thing I just want to explain. Let me explain there's a term, because there's one numerical question which I will be taking. There are two numerical problems which I will be solving. So, one is related to LMTD. So, there's a term called LMTD. LMTD, that is logarithmic mean temperature difference. This is normally used when we design a heat exchanger. So, this is the average temperature of the fluids. There are two fluids, hot fluid and cold fluid. So, the hot fluid is being cooled. Capital T1 is the temperature of hot fluid at inlet. Capital T2 is the temperature of hot fluid at outlet. Sometimes in some books or the data book, they will use hot fluid as TH, inlet is I, and this is for hot fluid, outlet is TH naught. Okay, so whichever the symbol we are using, you have to use it uniformly. So, this is for hot fluid. And for cold fluid, similarly for cold fluid, okay, for cold fluid, let me write it here. For cold fluid, small T1 temperature of cold fluid at inlet, and small T2 is the temperature of cold fluid at outlet. Sometimes this will be, in some book they will use TCI and TC naught. T stands for cold, I stands for inlet, and O stands for outlet. Let me complete this lecture at this point. I will be continuing the numerical questions. Two numerical questions will be solved in the next lecture, that is part 2. Thank you.